Hello there, Mr. Sutton here, bringing you the IM3 Chapter 4 Quiz 2 Review Solutions on Advanced Quadratics. To graph a function in intercept form, which is what we have here, we need to find the zeros first, because that's the easiest thing to find. Just whatever zeroes out each of these parentheses and makes the whole function equal 0. That'll give us x-intercepts to work with. So we have zeros of 2 for that first parentheses and 6 for the other one. Now that we found these, we can actually graph them out. So those are the x-intercepts 2 and 6. So that's already 2 points, but we need 3 points. And the third point is the most important one. That's the vertex. The vertex is always going to be halfway between points that are at the same y value. So basically, you just have to average these two zeros together, and that gives you the x value of the vertex. So doing 2 plus 6 over 2, that'll give us the x of the vertex again. That's 8 over 2, which is 4. So that's the x value of the vertex, and it's also the axis of symmetry. It creates a nice little line of symmetry for our parabola. Now, to find the y value of the vertex, we need to plug this x value back into the original function up here. So we've got y equals 4 minus 2 times 4 minus 6, and this is the y value of the vertex here, so I put a little v down there. So that's going to be 2 times negative 2, which gives me negative 4. And now I can graph my vertex of 4, comma, negative 4. So that's going to be over 4, down 4, right down here. And then just draw a parabola going through those 3 points. To graph something that's in standard form, we need to use the negative b over 2a formula to get the vertex of the parabola. So this will give us the x value specifically of that vertex. So that's going to be negative 4 in this case, because 4 is the number next to x. That's our b value. Over 2 times the a value, negative 1. So this is negative 4 over negative 2, which is positive 2. So that is the x value of the vertex, also the axis of symmetry, which we're going to use later on. But we still need the y value of the vertex. To get that, we plug this x value back into the original expression. So we have negative 2 squared plus 4 times 2. So that's going to be negative 4 plus 8, which gives us positive 4. So then our vertex is 2, comma, 4. And we can go ahead and graph that out. So we have 2, comma, 4 right up there. Now we need 2 more points. Usually one easy point to get is the y-intercept. The y-intercept you can find by just plugging in 0 for all the x values, and then you're just going to end up with whatever the constant is that's being added at the end here. Now, in this particular problem, it's a tough example because you don't see a number there. That means there's an invisible plus 0 out here. So then our y-intercept is going to be 0. Specifically, 0, comma, 0. It's going to be 0, comma, whatever this c value out here is. So that gives us a point right here. And now to get a third point, we're going to use symmetry. We have an axis of symmetry going through the vertex right here. So if I'm 2 to the left of that axis of symmetry to get that y-intercept, I just need to move 2 to the right at the same height. So there's another dot right there. And now we can graph our parabola through those 3 points. To graph this quadratic inequality, we're going to start by getting the vertex. Basically just pretending we're graphing a quadratic equation. So we've got negative b over 2a. That'll give us the x value of the vertex. That's going to be negative 4 over 2 times the a value, negative 1. So that's positive 4 over negative 2, which gives us negative 2. And now I need the y value for the vertex, so let's plug negative 2 back into the original. And I'm going to write y value of the vertex equals, not less than. I'm just going to turn this into an equation. Equals negative 2 squared minus 4 times negative 2 plus 3. So this is, let's see here, this is 4 if I square negative 2, but then it becomes a negative 4. We're adding 8, so negative 4 plus 8 is 4. 4 plus 3 gives us 7 for that y value. So negative 2, comma 7 is that vertex. Now before I start putting dots on this graph, I need to figure out, are they solid or open dots? And to see that, I look at the type of inequality that we're using. If the inequality does not have an equals, like this one does not have an equals, then we use open dots and dashed lines. If it did have an equals, then we would use solid dots and solid lines. But since this does not have an equals, we're going with an open dot. So negative 2, comma 7. Here's 4, 5, 6, 7. Open dot at negative 2, 7. And now, just like graphing a normal parabola in standard form, we get the y-intercept. That's going to be this constant plus 3 right here. So our y-intercept then is 0, comma 3. And I'll put an open dot at 0, comma 3 right down there. And then I'll use symmetry to get another dot on the other side of the vertex of the axis of symmetry right here. And we have a dashed line going through those open dots. So there's my dashed parabola, showing that the parabola itself is not actually part of the solution. Now we need to shade. And to figure out whether I'm shading above or below the parabola, I again look at my inequality. Since this is less than, that means we shade below, underneath the parabola. So that's going to be down here that gets shaded. Now, if this had said greater than, we would have shaded all this stuff above the parabola. And while we're on the topic of inequalities, one little trick you can use to see if a certain point is part of the solution, for example, if we want to know if 0, 0 is really part of the solution to this thing, is you can just plug the point into the inequality. So if I plug in 0 for y, and I plug in 0 for x, I would have the inequality 0 less than 3. And since that inequality is true, that proves to me that 0, 0 should be in whatever area you shaded for this thing. For this problem, we have the height in feet of a rocket after t seconds, given by this h formula. We want to know how long it takes the rocket to reach its maximum height and what that height is. So in general, when you're trying to find the max or the minimum of a quadratic function, you basically need to find the y value of the vertex. That will either be the highest or the lowest point of the parabola, depending on whether it's opening up or down. So to find the vertex of something in standard form here, we're going to go with negative b over 2a. That'll give us the x value of the vertex, or I guess in this case it's the t value. So I'm going to write t sub v equals negative b over 2a. So that's going to be negative 664 over 2 times that a value of negative 16. And let me go ahead and use the calculator for this. So here I am on the calculator, and to get that fancy fraction mode, I just did alpha y equals and picked n over d. So pressing enter on that, I get some crazy fraction. I'm going to go to math and turn that into a decimal. That's option 2. That's 20.75. And since I just found a t value, the unit on that is going to be seconds. So it takes 20.75 seconds for us to reach our maximum height. Now, what is the maximum height? Well, that's whatever I get when I plug in 20.75 to this h function here. So let me go ahead and do that. I'll replace t with 20.75 in the h function, all of that stuff there. And of course, I'm going to use the calculator for this. So crunching all those numbers on my calculator, I get 7,889, and that is going to be in units of feet. For this problem, we have 200 feet of fencing to make a rectangular enclosure, and we're using the side of a building as one of the sides of the enclosure. We want the dimensions of that enclosure that give us the greatest area, and also what that area actually is. So it's a good idea with these area problems to start with a picture. In this case, it's an easy one, just a rectangle. And one side of this enclosure is the building itself, so we don't count that when we're using our fencing. And now, at some point, I'm going to have to make a formula for the area of this enclosure, and I'm going to have to maximize that area. So to get the area formula, I need to talk about the length and the width of this, and it'd be nice if I had only a single variable to work with. So I'm going to make this side of the building x, and I'm going to try to express everything in terms of x. So this other side also has to be x because it's the same length, but how about this third side? Well, if I have 200 feet of fencing to work with, and I've used up 2x of it, that means I have 200 minus 2x left over for that last side. So now that I've got everything expressed in terms of x, let me write my formula. So for area of a rectangle, that's length times width. In this case, length is 200 minus 2x, and the width is just this x here. And at this point, I have to maximize this parabola formula. So to do that, just like anytime we're trying to maximize something with parabolas, we're trying to find the vertex. Specifically, we're going to start by finding the x value of the vertex, and then we'll move on to see what the output is, and the output in this case is actually going to be the area. So when you have something in intercept form, the easiest way to get that x value of the vertex is just to find the zeros and then average them together. So the zeros for this first parentheses, if you subtract 200 and divide by -2, that's 100 for that 0. And this factor of x gives us a 0 of, well, just 0. So if I average those together, that's going to give me the x value of the vertex for this parabola. It also happens to give me the width because the width is exactly x. So I'm going to write width at the vertex equals x value of the vertex equals 100 plus 0 over 2. So that has a value of 50, and that's units of feet. And I'm mentioning the width in here because they did say they wanted the dimensions. So I have to say what the width is, I have to say what the length is, and then I have to use that to say what the area is. So next, let's find the length. That's going to be 200 minus 2 times x. In this case, 2 times 50. So 200 minus 2 times 50. That's 200 minus 100, which is 100 feet. So that's the length of the ideal rectangular enclosure. And to get the area, there's a lot of ways to do it. You could plug in x to this formula up here, but you actually already found the length and the width. So why not just multiply the length of 100 times the width of 50, and that gives us 5,000 square feet.